वेलकम बैक फिजिक्स एंथुसियास्ट। आई एम स्वाति एंड आज का वीडियो है डेरिवेशंस पे। तो जो भी इंपॉर्टेंट डेरिवेशंस है फ्रॉम करंट इलेक्ट्रिसिटी विल डू इन दिस लेक्चर। लेट्स बिगिन विद दैट। ओके, सो चैप्टर 3 करंट इलेक्ट्रिसिटी के अंदर अपन ड्रिफ्ट वेलोसिटी, रिलेशन बिटवीन करंट एंड वीडी, डिडक्शन ऑफ ओम्स लॉ, ठीक है, ये करेंगे। देन कॉम्बिनेशन ऑफ सेल सीरीज एंड पैरेलल में कंडीशन फॉर मैक्सिमम करंट एंड प्रूफ ऑफ व्हीटस्टोन ब्रिज। तो ये मैक्सिमम इंपॉर्टेंट डेरिवेशंस हैं, इसको आज के लेक्चर में अपन कवर करते हैं। सो फर्स्ट इज ड्रिफ्ट वेलोसिटी। ओके, सो अगर हम ड्रिफ्ट वेलोसिटी की बात करें तो ये वो वेलोसिटी होती है जो इलेक्ट्रिक फील्ड की वजह से पार्टिकल गेन करता है, इलेक्ट्रॉन गेन करता है। वेलोसिटी अटेन्ड बाय द इलेक्ट्रॉन्स in the presence of electric field, in the presence of electric field, ठीक है। तो इलेक्ट्रिक फील्ड जब लगी तो उस पे इलेक्ट्रॉन पे एक फोर्स लगेगा, उस फोर्स की वजह से वो एक पर्टिकुलर डायरेक्शन में मूव करेंगे एंड दे अटेन एन वेलोसिटी, दैट एवरेज वेलोसिटी is basically your drift velocity. Okay, so we can now state that consider a conductor of area of cross section A and length L. ठीक है, और लेंथ अपन ने L मान लिया। तो कंसिडर करो ये एरिया ऑफ क्रॉस सेक्शन ऑफ अ कंडक्टर है, ठीक है। अब कंडक्टर के अंदर फ्री इलेक्ट्रॉन्स तो होंगे ही, एंड क्योंकि कोई करंट, कोई एक्सटर्नल सोर्स नहीं है, सॉरी, इसका एरिया हमने मान लिया A और इसकी लेंथ हमने मान ली A। अब इन द एब्सेंस ऑफ इलेक्ट्रिक फील्ड, इन द एब्सेंस ऑफ एनी external source, that is electric field, electrons are in random motion, electrons are in random motion. Okay, one electron is moving here, one electron is going there, one is up, one is down, so everybody is in some different direction, so the average velocity would be 0. ठीक है, electrons are in random motion, so the average initial velocity of the electrons क्या हो जाएगी? अगर हम U एवरेज देखें तो दैट मीन्स इंडिविजुअल इलेक्ट्रॉन की वेलोसिटी का सम करके अगर हम उसका एक एवरेज लेते हैं, दैट कम्स आउट टू बी 0 बिकॉज डायरेक्शन आर इन रैंडम। सो तुम्हारे पास जो U एवरेज आया दैट इज 0 इन द एब्सेंस ऑफ इलेक्ट्रिक फील्ड। Okay, now this conductor is attached to some source and then net field, external field is applied to it. So when the conductor is connected to some external source, and an electric field is applied across it. Okay, so due to the electric field, the particles will attain an acceleration because the force will applied on it, and it will give some acceleration to the electron, due to which the velocity will change, and that average velocity is a drift velocity. So due to the force acting on electrons due to electric field, an acceleration is developed. Okay, और वो एक्सेलरेशन जो होगा वो इलेक्ट्रिक फील्ड के अपोजिट डायरेक्शन में होगा, बिकॉज इलेक्ट्रॉन पे जो फोर्स लगता है वो अपोजिट डायरेक्शन में होता है। in the direction opposite to electric field. Opposite to electric field. So now if the force is equals to EE and the force is also equals to mass into acceleration, then ये तुम्हारा कूलम्ब्स लॉ या इलेक्ट्रिक लॉ के रूल से है, ये तुम्हारा न्यूटन्स लॉ के अकॉर्डिंग है. सो देन ma is equals to ee and then acceleration is equals to ee by m with a minus sign and negative shows opposite direction. Okay. Now, due to this acceleration, the velocity will change. Due to this acceleration, electrons will move in a particular direction with some velocity. Electrons will move in a single direction, with some final velocities के साथ. Final velocities given as v1 is equals to u1 plus a t1 and that t1 is replaced as tau1 and we define tau1 as relaxation time. v2 as this is u2, this is u1, this is u2 plus a tau2 and so on. ठीक है, till vn is equals to un plus a tau n, where tau is the relaxation time. That is the time between two successive collision. Time taken between two successive collision. Okay. So if we take the average of this velocity, average of the final velocities give drift velocity. So if I take Vd, then it would be V1 plus V2 plus V3 till Vn upon n. Okay, and your V1 is what? U1 plus a tau1 plus U2 plus a tau2 and so on by n. You can n को bifurcate कर दो, that Vd is equals to u1 plus u2 till un by n, right? Plus a is common, tau1 plus tau2 till tau n by n. Okay, and this is your initial average, which is 0. This is acceleration and this is tau average. We have written as tau. Okay, the new average is 0 and acceleration is minus ee by m into tau. So from here Vd comes out to be as minus ee by m into tau, where negative sign gives the opposite direction. That is, this average velocity is in opposite direction of electric field. So negative sign shows that Vd is in opposite direction of E. Opposite direction of E. Okay, now in this only if you have to calculate the current, the relation of current, then what you will do, second is, we'll continue from this only, relation between current and Vd, relation between current and drift velocity. So in this, because we have to calculate the drift velocity, so just connect this conductor with a battery. Okay, and here also when it is connected to this, you can show that it is connected to some battery. Okay, now the conductor is been connected to some external source, which is a battery, and which applies some electric field. Okay, so for the current only, we have already connected it to the battery, and an electric field is set up like this, and the electrons will move in opposite direction. Okay, so here it's very easy that consider a conductor of cross sectional area A, of cross sectional area A, and length L. Okay, so this is L length and its area is A. Okay, and let's take small n as number density of free electrons, that is number of electrons per unit volume. So total number of electrons would be what? Number density into volume, n into volume, and that volume is A into L, area into length. Fine. And if this is the number of electrons, then you can calculate the total charge. So total charge in the conductor of area of cross section A and length L would be E times of this total number of electrons, that is E times of NaL. Okay, now you have the charge, and you can calculate current. Okay, so for the current, it is charge per unit time, and for the drift velocity, you can calculate that distance is equals to velocity upon time. So from there you can calculate the time. So time taken by electron to travel the distance L, to travel the distance L, because here the length of the conductor is L, so the electron has to cover the distance of L. So time would be what? Distance upon velocity. So distance is L and velocity would be Vd. So we can say that time taken by electron to travel the distance L with velocity Vd in the presence of field. In presence of field, because in the presence of field it only moves with drift velocity, so the time would be L by Vd. So now the current in the circuit would be I is equals to Q by T, and you just put the value of charge Q, which is E N A L, and time is L by Vd. So L is here, Vd goes up. You can cut L by L. Then your current comes out to be NeaVd. NeaVd, which is very, very important relation. You can get some numerical on this relation, or directly they can ask. So this particular relation is very important. And if you just put A to B here, then current per unit area will gives you J, that is current density. And that current density comes out to be what? NeVd. NeVd. Okay, so they are the important relations which whose derivation is important. So if we have to find the deduction of Ohm's law, so we can start it with this relation only. So deduction of Ohm's law, because this is the basic thing, that we have a conductor which has some area L and area A and length L, and it says number of density, and we have simply used the basic principle of charge and current and stuff. So from there only we can deduce this Ohm's law from the basic principle. So for that only we know that I is equals to NEAVD. NEAVD. Okay. So just put the value of VD here. The magnitude, just forget the negative sign, the direction. E by tau into M. Okay. Sorry, E tau by M. Fine. Now this is I, and this N E square tau by M. Just take all these constants to be out, because n number density will be fixed. E is the charge fixed, tau relaxation time fixed. T, tau and N can change if you change the material of a conductor, or if you change the temperature, because temperature can change the relaxation time. The collision becomes more frequent, the relaxation time will change. Number density will also change, because there would be some breakage of covalent bond. So otherwise this whole term will remain same. Now you have A and E. Okay, what we will do, we will divide it by L and multiply it by L. Okay, and this E into L gives you what? Voltage. Tau by M. So A by L, take as constant here, and this EL, the electric field in a particular length, gives you potential across that conductor, across that length L. And if you just divide I here and take the whole term here, then it becomes M upon N E square tau L over A. And you can see that this whole term is a constant for a particular condition. If the temperature is fixed, material is fixed, length and area is fixed, then whole term is constant. So this is constant for particular dimensions of a material at any given temperature. And that's what Ohm's law has said, that V by I is a constant at a particular temperature. So V upon I comes out to be constant, and that constant is then written as resistance, and this is what? Ohm's law. This becomes your Ohm's law. Okay, so from here R comes out to be what? M upon N E square, M over N E square tau L by A, and this quantity again is a constant for any particular material and temperature. So this is known as rho, which is specific resistance or resistivity. Specific resistance, or you can say resistivity, which only change when you change the temperature or the material. Okay, and the reciprocal of this resistivity will gives you sigma, which is conductivity. Okay, so these are the basic relation which I have explained you, and it comes one after the. Okay, next we'll move to cell. Okay, the combination of cell. Okay, so the next is your combination of cell in series and parallel. Combination of cells. Okay, so in this first we'll see in series combination. So in series combination, basically it's very easy. The positive terminal, let's say the negative terminal is connected to the positive terminal. This is how a series combination work. Okay, so let's take a cell system of cells, a system of two cells of EMF E1 and E2 having resistance R1 and R2. Okay, and we have to calculate the equivalent EMF of this combination. It's very easy. Just mention the points A, B and C. You must know the relation between terminal potential, EMF, internal resistance and everything. It's very important. Okay, so consider two EMF having EMF of E1, two cells of EMF E1 and E2, two cells of EMF E1 and E2, and internal resistance R1 and R2 respectively. Internal resistance R1 and R2 respectively. Okay, and net current I is flowing through it. It goes from positive to negative, so the current would be like this. Okay, and current I is flowing through it. Is flowing through it. Okay, so now what we will do, we will calculate the potential difference between A, B and C point mein. So potential difference between A and B. First, तो V A B A and B में निकालना है. So A is at higher potential because current is flowing from B to A. So it would be VA minus VB. VA minus VB, and that is equals to EMF minus IR1. That is E1 minus IR1 from the relations from EMF and internal resistance. You must know that. Mark this equation as 1. And then we can calculate the potential between B and C. Potential difference between B and C. Again, the current is flowing from C to B. So it's like VB minus VC. VB minus VC is equals to E2 minus IR2. Mark this as second. Okay. So if we made the equivalent circuit for the equivalent circuit, basically that two cells will give you a net effect. So this is my equivalent EMF with equivalent internal resistance between A and C. That two cells gives the combined effect. So here the equation will become, for the equivalent circuit, it's VA minus VC again, and that is equals to E equivalent minus IR equivalent, because the current will remain same. And if you remember, then the series thing, it is given that the current through individual device is equal to the total current of the circuit. So I will remain same. Mark this as equation 3. Now if you simply add 1 and 2, add equation 1 and 2, you can simply get that VA minus VB plus VB and minus VC. Okay, and that is equals to what? E1 minus R1 plus E2 minus R2. We are simply adding both the equation. E1 minus IR1 plus E2 minus IR2. Okay, now this VB and VB cancel each other. Then it becomes VA minus VC. And just take E1 and E2 to be together. E1 plus E2. And let's take minus I common here, and R1 plus R2 again together. And mark this as equation number 4. Okay. Now, if you compare equation 3 and 4, you can see that E equivalent is equals to this value and R equivalent is equals to this value. On comparing equation 3 and 4, 3 and 4, your equivalent is equals to E1 plus E2. That means whatever be the number of cells, just add all of them and you will get E equivalent, and your R equivalent is equals to R1 plus R2. Now, the cells have polarity of plus and minus. So if one of the cells is arranged, there's a condition. If one of the cells is arranged in an opposite polarity, that is negative is connected to positive, negative is connected to positive, and somehow one cell is in opposite, right? So what you have to do, you have to subtract the EMF of this particular cell. This is E1, E2, E3, E4, E5. So here the equivalent will gives you E1 plus E2 plus E3 minus E4, because it's connected in opposite polarity. E3 minus E4 plus E5. Okay, but for the resistance, it is simply R1 plus R2 plus R3 plus R4, because internal resistance has no polarity. Plus R3 plus R4 plus R5. Okay, so now in this particular scenario, if we need to find the maximum current, if you have n number of cells are connected, and what should be the condition between capital R, external resistance and internal resistance, so the maximum current can flow. So for that, we can say condition for maximum current in series combination. So you can say that consider M cells are connected in series. Okay, so if M number of cells are connected in series, let's say M, okay, and they are connected in series to some external source, or you can simply say to some resistance R. The external resistance is capital R. ठीक है, तो M cells are connected in series, each having EMF E and internal resistance R. And internal resistance R. Okay, then equivalent for this would be E plus E plus E till M times. So M times E, and again the resistance is R plus R plus R plus R till M times, then it would be M times R. Okay, so the equation of current is what? Equivalent upon R equivalent plus external resistance. This is the equation. Then it becomes ME by MR plus capital R. Now, here you can take two conditions. First, take MR to be very, very greater than capital R. So, if capital R is very small, then you can neglect it and your I would become ME by MR. Okay, because capital R is very small, so you can ignore it. It becomes E by R. That means E by R will give me current due to single cell. This is like due to single cell, that means the value is less because it comes out due to single cell. And if your MR is very small than capital R, then you have to ignore MR. Then here the I will become ME by capital R. Okay, my device There is some glitch. Okay. So now you can see that this E by R is M times, means all the M cells which are connected in the circuit gives its effect due to all the M cells. Due to all the cells. All the cells. So if it is due to all the cells, then this is what? Maximum current condition. So in series combination, your capital R should be greater than small r to get the maximum current. Okay. Now we will see what will happen in parallel combination. Okay. So the second is in parallel combination. In parallel combination, your positive terminal of cell is connected to the positive terminal of another cell. It is something like this. It is connected to this. Okay. Here that positive, negative in series, and in parallel positive to positive, negative to negative. So it is something like this. This is the combination. Let's say this as A, this is a C, or you can take B. Okay. This is EMF E1 and internal resistance R1. This is EMF E2 and internal resistance R2. Okay. So consider two cells of EMF E1 and E2 having internal resistance R1 and R2 respectively. Having internal resistance R1 and R2 respectively. And now it is in parallel combination, so the current would be different. Let's say here the current is I1, here it is I2, it combined together and the I current is flowing in the equivalent circuit. And current I1 and I2 flowing across E1 and E2. Across E1 and E2. Okay. So now the potential difference between A and B is same. So you can simply, it's moving from B to A. So potential difference between A and B is VA minus VB. VA minus VB, and that is equals to E minus IR1. So it is E1 minus I1 R1. Let's see V and VB to be V. Okay, because it remains same for both. And from here you can calculate this I1. So take I1 R1 to be here. It becomes E1 and minus V, and your I1 will give you E1 by R1 minus V R1. Mark this as equation 1. Similarly, for cell 2, VA minus VB. Again, this is also in between A and B. It would be E2 minus I2 R2, and VA minus VB can be written as V. And from here you can calculate I2 as E2 minus V over R2 by R2. Fine. Now here the total current in the circuit, total current in the circuit, basically I is equals to I1 plus I2. I1 plus I2, and that I is equals to E1 by R1 minus V by R1 plus E2 by R2 minus V by R2. Okay, just take even terms together and take minus V, 1 by R1 plus 1 by R2. Okay, now we will calculate it for the equivalent circuit. and we compare that. Mark this as equation 3, and then for the equivalent circuit, that is between A and B, you have E equivalent with R equivalent, and the current flowing is I. So here the equation would be the potential is again VA minus VB, which is equals to E equivalent minus I R equivalent. Again VN minus VB can be written as V, so your I can be E equivalent minus V upon R equivalent, and R equivalent, mark this as equation 4. Now if you compare equation 3 and 4, on comparing equation 3 and 4, this E equivalent by R equivalent is equals to this, and 1 by R equivalent is equals to this term. So your equivalent by R equivalent is E1 by R1 plus E2 by R2, and so on for a number of cells, and 1 by R equivalent is equals to 1 by R1 plus 1 by R2. It's same like as we did in parallel combination. Okay, so from here you can calculate R equivalent, which comes out to be R1 R2 upon R1 plus R2, right? And we can substitute that value in the first part. So here equivalent by R equivalent is equals to, take LCM, so it's R1 R2, sorry, E1 R2 plus E2 R1 upon R1 R2. And you can substitute R equivalent, the value of R equivalent in the equation. R equivalent moves here, and you can just put the value of R equivalent as R1 R2 over R1 plus R2. These two terms will cancel each other, and your equivalent comes out to be E1 R2 opposite multiply plus E2 R1 over R1 R2. This can be achieved using, if you have two cells in the circuit, then it is easy to use. Otherwise, use this formula. For a number of cells, E1 by R1 plus E2 by R2 plus E3 by R3 till En by Rn, R equivalent 1 by R1 plus 1 by R2 plus 1 by R3 till 1 by Rn. This is for two cell system. Okay. Now again in this also, if we need to calculate condition for maximum current, so what we will do, so consider n cells are connected in parallel, okay, each having EMF E, each having EMF of E and internal resistance R, and internal resistance R. Okay, so now one cell is connected to another cell, and n number of cells are connected to an external resistance capital R. Okay, and this is connected to an external resistance, capital R. Okay, now since each having a EMF of E and internal resistance R, so equivalent EMF would be E only. Why? Because you have R thing also, E1 by R1 plus E2 by R2. If you add all those things, then it eventually gives you E only. And for R equivalent 1 by R1, so this single R is divided by N. Okay, so total current in the circuit, or you can also say that in parallel EMF is same. I is equals to E equivalent upon R equivalent plus external resistance. So E equivalent is E. This is R by N plus capital R. Okay. If you take the LCM here, then this becomes NE. This is R plus NR, and that denominator N will goes to EMF. Okay. Now, if we take two condition, first, internal resistance is very greater than external resistance, then your current would be NE by R due to N cells. And if it is due to N cells, then the current would be maximum. So this is the maximum condition. And if R is less than this, then you can ignore the small r, internal resistance, and that comes out to be E by R, that is due to single cell. Okay. So for the maximum condition in series, the external resistance should be high, and in parallel, the internal resistance should be high. Okay, now we will do the last derivation of this lecture, that is proof of Wheatstone bridge using Kirchhoff law. If you have any doubt, any query, you can comment below. I will help you out with that. Okay, so Wheatstone bridge comprises of 4 resistance connected like this. Okay, it has a galvanometer here and a battery is connected here. This is galvanometer. Mark this resistance as P, Q, R, S. Now it has a condition that if there is no deflection in this galvanometer, that is the current in galvanometer is 0, then P upon Q is equals to S by R. That means the resistance in the 4 arms are in equal ratio. And vice versa. That is, if the resistance of 4 arms are in equal ratio, then the current across galvanometer is 0. So the condition of Wheatstone bridge is that is, if Ig is 0, that is, there is no deflection in galvanometer, then P upon Q is equals to S by R or R by S, anything. If I have mentioned S here, then S by R, and vice versa. That means if the condition is there, if the resistance in the 4 arms are in equal ratio, then the current across galvanometer is 0. So I will prove this condition using Kirchhoff rule. So if this is my Wheatstone bridge and it is connected to some external source, then let's say if current I is flowing from here, I, let mark as P, Q, this is S, that is R, and the galvanometer is here. Okay, so what we can simply do, that I current is flowing here. Let's say some current is divided in this branch, that is I1. Okay, so the current moves in this branch would be I minus I1, or you can simply use I2. It can anything. Then let's take it as I2, because the less variables you have, the more easy for you to solve it. And then some current will flow here, Ig, and then that current will be reduced from I2 in the branch Q. And when the current is moving towards in the branch R, then this I1 is added to Ig. I1 plus Ig, and then I1 plus Ig plus I2 minus Ig will gives you I1 plus I2, which is I. As this, at this point, I break into I1 and I2. Okay, and then you have just put the Kirchhoff thing. So with this, I can also explain the Kirchhoff law. So first, you can take the loop ABDA, and there is a tip. If you are taking it a clockwise direction, ABDA, then the other loop should also be clockwise. Then all the loops should be in clockwise. If you take first loop as anti-clockwise and take all other loops as anti-clockwise, then your answer would be correct. So if we take the first loop ABDA, and then from A to B, you are moving in the direction of current, take that as positive. So the resistance is P, current is I2, then it would be PI2. Okay, then from branch B to D, again you are moving in the direction of current, then is GIG plus GIG. Then from D to A, you are moving against the direction of current, then it would be minus I1S. Take the whole term to be 0, okay? And then take the loop BCDB. In loop BCDB, mark this as 1. Now from B to C, you are in the direction of current, and it would be resistance Q into I2 minus Ig. Okay. Then from C to D, in the opposite direction of current, so minus R I1 minus Ig. And then from D to B, opposite direction, so minus GIG. Minus GIG. Okay. Now taking the condition, taking the balanced condition of Wheatstone bridge, that is Ig equals to 0, then equation 1 would become Pi2 and Ig would be 0, so this term would be 0 minus S I1 equals to 0, then Pi2 is equals to Si1, mark it as equation 3. Okay, and equation 2 would become what? Again put Ig to be 0, Ig here 0, then it would be Qi2, then here also it is 0, then minus Ri1, and again this Ig is 0, so it's 0. So Qi2 is equals to Ri1, mark it as equation 4. Now simply divide equation 3 and 4. It's very easy. If you know Kirchhoff, you can solve it like in a minute. So Pi2 over Qi2 equals to Si1 upon R I1. I1 cancel, I2 cancel, then P by Q is equals to S by R, the condition of balanced Wheatstone bridge. Okay. So if you know the Kirchhoff law, and Kirchhoff is very easy, all you have to know is to just mark the direction of current. If you know that, then it's like a win-win situation. Okay, so this is much for your current electricity. These are the important derivations, and if you have any query, anything, you can comment below. I will help you out with that. And thank you for watching this video, and do like, subscribe and share. And the next video would be on MCQ on moving charge and magnetism.